So today we'll continue with the exploitation of the properties of the Christophanian symbol, or what we always call the affine connector. Now, first of all, we are given an expression here, given that gamma mu alpha mu is equal to minus 1 over 2 g mu comma alpha. We are supposed to show that the derivative of this with respect to that should give us that. Of course, by g mu comma gamma we mean the g mu, the x gamma. So you can see that what we have here as g mu comma alpha is the same as the g mu, the x alpha. In other words, we have something similar here with that. So just like we will always do whenever we are solving such problems as this, we are going to try as much as possible to consider the objects with which we are differentiating with respect to. For instance, in this case, you have that the gamma mu alpha mu, the g, what we have is mu comma gamma. This is the same thing as this doesn't in any way look like what our variable is or what we are differentiating with respect to. This doesn't have any derivative with respect, and besides it's also a covariant object. Well, we can try to make them all contravariant, but that is if it has a derivative, but in this case it doesn't. So all we have is simply minus half g mu, the g mu comma alpha, the here g mu comma gamma. Yeah, so this turns out to be quite simple. As we can see, everything else on top here for the indices are the same, except of course for the gamma and the alpha. And if they were all to be the same, this would simply just be 1, but they are not. So because of that, this object gives us a chronicle delta of alpha gamma. So in other words, what we have is simply minus 1 over 2 g mu delta alpha gamma, just as required. So this was quite a very simple case. Now we have something a little more involved than this in the next one that we are going to show. Leaving this just for a while. Now looking at this, we have here the g mu gamma alpha mu. Here we are differentiating this with respect to g rho sigma comma gamma. Well, as a trick that might help us to solve this problem, we might, for instance, consider something like this: g alpha beta covariant derivative with respect to mu. By our standard of definition for a covariant derivative, this will be g alpha beta the x mu, then plus, because I'm dealing with contravariant indices. I'm contracting alpha now with nu, taking alpha to this. What I'm differentiating with is mu, and this is g nu beta plus. I am here contracting beta, so I put beta to this side just along the same line as usual. I leave alpha where it should be, but then I replace this with the dummy index nu, and again I'm differentiating with respect to mu. Okay, well, here this is what we have, and again, of course, that is what we will expect, because we always contract with and we're differentiating always with respect to this, but this is what we get in this case. Of course, in general, we know that this, for instance, is always equal to 0 for the metric tensor. That's the covariant derivative of the metric tensor. That is always equal to 0. And we can represent this by saying g alpha beta comma mu. So in other words, g alpha beta comma mu plus this, mu alpha g nu beta plus gamma beta nu mu g alpha nu is equal to 0. Okay, we are just looking for a means here by which we can try to express this into something manageable. Yeah, something in which we can, if possible, we'll just make it all in terms of either a product of this and stuff like that. So in other words, at this point, what we can try to do is to contract beta and mu. In other words, we can say set beta to be equal to mu. What will this result to? We are going to have here g alpha mu comma mu plus gamma nu mu alpha g nu mu plus here gamma mu. So I'm just making sure that all the betas have been changed to that. alpha nu is equal to 0. So every beta that we have along have been changed to mu. Now you can see something here quite magically. Well, you can see that we can make this the subject of the formula nu mu g nu mu, just to make it desperate to make that exactly that. This is the same as minus g alpha mu, comma mu, minus gamma mu nu mu g alpha nu. That is what we get. Well, this is beginning to look much like it. This was a problem because all these indices were all different. This is not a problem because we have a dummy index attached to this affine connector. And we know it's not a problem because it means we then can write it in this form. And being in that form, as you can see, it means it's also just in terms of a product of this and such objects as that. So all we are going to do is to take this now and put in place of that. So this implies that the g mu nu gamma alpha mu nu, the g here rho sigma comma gamma is the same thing, of course. So I'm going to go straight forward. The g alpha mu comma mu, the g here rho sigma comma gamma, then minus. Of course, here again we have a situation. This again isn't exactly like this object, so I'm simply going to put this, and this is going to be the mu nu mu, and this is the g rho sigma comma gamma. Now, for some reason here, I may want to make a change. I may want to make a change on this term, and the change here is interchanging mu and nu. Mu and nu. That is, of course, first of all, we know we can do that because we have them both to be dummy indices. Second of all, why do we want to do this? From our understanding of what this object is, gamma mu nu mu is the same thing as 1 over the square root of minus g, d, the x, always the one that is a free index or the single one, minus g. So the derivative with respect to will be with respect to x nu. But you understand, of course, that supposing I decide to make this change, what I will have on this Christoffel symbol or affine connector will be quite different. What is it going to be? It's going to be nu, mu, nu. And if that is the case, then this derivative will be with respect to mu. And if it is with respect to mu, then I have things here to be uniform, because you see, the derivative I have here on the first term is with respect to mu. So in order to make things quite a little more elegant and manageable, it's always better to work with terms such that they are all derivative with respect to the same object. So in other words, considering that we can make this transformation, I'll rather make that substitution to be such that this, in essence, will be replaced rather with nu, mu, nu. So that in the end, of course, it will be quite easier for me to manage. Good. So after obtaining this expression, the next thing we will want to do, for instance, will be to address or solve each and every one of these one after the other. Looking at the first case here, I think the first one there, the easier one there would be this. Let's deal with that first. That is the gamma nu mu, I believe. Yes. The gamma nu mu down, or whatever. So of course it's symmetric, so it doesn't matter which comes after the other. And here this is the g rho sigma comma gamma. Again, I hope that is the right thing exactly. It is. So in the case here now I could do something. I was given here that gamma mu alpha mu is the same thing as minus 1 over 2g mu nu g mu nu comma alpha. Well, I don't see why this should have been up actually. Well, but it doesn't matter because even nu here is also contracted. Mu nu are also contracted. So the only index that stays on both sides of the equation is alpha alpha, both of which are not contracted. But note that I could have written this as minus 1 over 2 some g alpha beta, comma. Okay, then it means I will have to. Okay, so let me just use the pair of indices. I think rho sigma would be good. So this could as well be rho sigma, comma alpha. and it will still be equal to this, because like we've noted, the mu here is contracted, so we don't have to look for some mu on the right hand side. We have an alpha here, which is a free index, of course, is also free there on the right hand side. So rho sigma are both contracted. In other words, this is just the same as that. But what are we talking about here really? What we're talking about here is we have an expression. This is nu, mu, nu. In other words, I could write this the same as minus 1 over 2 g rho sigma, g rho sigma, alpha. No, not alpha, it can't be alpha this time around. It must be the mu, which is not contracted. It must be the mu. What we are trying to look here for a situation whereby we can exploit this contraction here that we have. Like I said, for this object, you might as well use this. And for the same object, it could have been eta z, whatever, just double indices that could be contracted. In the end, it wouldn't affect our expression. But the alpha here must all be represented. So like you can see here, mu here. So I could use rho sigma, if I prefer. I have mu here. It could have been also mu nu. No. Okay, I can't make mu, but it could have been mu something and something else, just to make sure that these two contract and there can be no recurrence on the left or on the right hand side. The important thing, by the way, is that when I am looking at this object here, I'm looking for a way to write it such that it could look as closely to this as possible. You note, of course, that if I do something like this, minus g, something like that, g and this eta, comma, the same mu. Of course, if I am to differentiate this object with respect to this, I'm going to have a lot of unnecessary chronicle deltas. Of course, rigorously, I should consider that and perform some symmetrizations, but that is not necessary at this stage. So if I can simply write this in this form instead of something like this, then it will be particularly helpful for my purpose here, because it means that I can simply say that the gamma nu mu nu is the same thing as the g rho sigma comma gamma, and so this will be the same thing as looking at this expression minus 1 over 2 g rho sigma, and then I have here with me the g rho sigma comma mu and the g rho sigma comma gamma. So can you see that now? So this was the reason for all the fuse around here. Now you can see I have rho sigma here, just to mimic what was down already. In other words, the whole thing is to make sure that this ends up being just the chronicle delta mu gamma. Just like we noted in solving the first problem, we have said then that if mu and gamma were the same, this would just be 1. Otherwise, the whole thing is 0. So in other words, what we have tried to do here is to have shown, and I think it would be good for me to just record that somewhere here, if I'm not going to be concerned about that just yet. So this is going to be derivative of gamma nu mu nu with respect to dg rho sigma comma gamma, and my result here is minus 1 over 2 g rho sigma multiplied here by a chronicle delta of mu gamma. Okay, that's that about that. Now the next thing we want to consider is this. We have stopped somewhere here in this expression. Fine. We want to consider the second, the first term there, which we left out because of some technicalities that just might be involved with this. This is g here, alpha mu, comma mu, and then we have it the g rho sigma comma gamma. And so at this point in time, we can see already that performing this derivative, well, first of all, we can try to take care of this contraction. This contraction is going to cause us a lot of confusion, because we can see even if we want to obtain the chronicle deltas, we have some sigma being equal to mu. The gamma will also have to be equal to mu. In other words, both sigma and... So to avoid all that, this is the same thing as the g alpha mu. Now, let me write that in something now. So what I intended to write was dg alpha mu, some delta, comma n, chronicle delta, okay. Well, it's okay. I think this is all fine. Rho, sigma, comma, gamma. So the chronicle delta has a delta as one of its indices. Well, the point here is this is the same as this in the sense that, of course, this expression is all zero unless, of course, delta is equal to n and maybe equal to mu. It could have been anything else here so long as it's repeated, m and whatever, so long as it's repeated. So these two indices have to be equal. So let me just go straight ahead and say this then should be the same as that. And so I have here dg alpha delta comma n, dg here, rho sigma comma gamma. Okay, now here comes something tricky. We know here that the metric tensor g alpha delta is symmetric. This is the same thing as g delta alpha. And, excuse me. And if we were to perform this also, we note also that what is down there, g rho sigma, is also the same thing as g sigma rho. So how are we going to do this pairing or equation? Excuse me. Okay, now consider this case. For instance, of course, the cases we have been dealing with so far, I tried as much as possible to avoid this technicality. But the point here is this. Supposing alpha, so you could have considered this object, for instance, the g alpha delta, comma n, the g rho sigma, comma gamma. You could have considered this by saying this is the same thing as some chronicle delta of alpha rho. Chronicle delta of here sigma delta. Of course, this chronicle delta, these two also, we have the chronicle delta for those two. Those two have to be equal. Yeah, indeed, of course, if alpha is equal to rho and delta is equal to sigma, and if n is equal to gamma, then this is equal to 1. Otherwise, it's 0. And these conditions have to be met. However, take note that this is also the same. Right? This is also the same as a situation. Okay, I think I should make that more apparent too, like the other one. Supposing I have written this, the g delta alpha, comma n, and then here the g rho sigma, comma gamma. What will this suggest? Now you can see here at this point that this also suggests some sort of delta, chronicle delta, delta of rho, chronicle delta alpha of sigma, chronicle delta, of course, the last one remains the same. It's still n and gamma here, nothing has changed about that. So if I do some kind of pairing between these two directly, you can see that I have to, and yet these two expressions are the same. Like we said, the two metric tensors are the same, whether or not we make those interchanges. Now, if that is the case, what then are we to do here? Because we obviously have a situation whereby, of course, these two are the same, but obviously these two are not exactly the same, because we have a chronicle delta here saying alpha will have to be equal to be rho for this to be non-zero. But here it's saying delta has to be equal to be rho for this to be non-zero. So we have a situation here, two possible options, and which has to do with the permutation of the indices on these tensors. And so this brings us to one of the ideas we have always mentioned, symmetrization of a tensor. And in order to symmetrize a tensor, let me do that somewhere below here, and I can continue with that later. If I want to symmetrize a tensor, for instance, I have v sub mu nu. To symmetrize this tensor will be to take an average over the permutation of these indices. This is the same thing as 1 over 2. And of course, that will mean I'll have to indicate this with some round brackets. That is the general convention, by the way. Mu nu plus v mu mu. This is what it will be. Of course, if there are three indices, I think we've mentioned this before, mu nu lambda, then I'll have 1 over 3 factorial. Then I'm going to have v mu lambda plus the cycles. The cycles, in other words, by cyclic permutations, which are 2 more, then plus. I'm going to perform an odd permutation, nu mu lambda. Of course, plus the cycles again. That is again a cycle of odd permuted objects of this kind. So, in other words, if we want to perform for the anti-symmetrization, it will simply mean this again, but then I'm going to use boxes here to illustrate that. This will be, for instance, 1 over 2, but then I'll have a minus. The circles for the first one here will all have plus. The ones here will all be minus. So let me just be explicit with this one, and so that I won't have one thing left undone here. This is V mu nu lambda plus V nu lambda mu plus V lambda mu nu plus, again, so the odd permutation, I have nu mu lambda. I can decide to come back again and say V mu, but then I perform it between lambda and nu, plus lastly, I perform that between the first and the last. So I bring lambda here, nu here, and then mu there. Of course, that's what this means. But like I was saying, for the anti-symmetrization, I will have to use a symbol such as this, mu nu. The only difference, I'll have a minus here. In this case, I'm going to have again something like, say, V mu nu lambda, and then the only difference will be minus here, minus here, minus here. But this is just the idea behind symmetrization. It happens for a case. So for instance, in this case, if these indices were symmetric in the interchange between these two, you know, of course, that you just have to add the 2 and you get 2, which is cancelled by these 2, you get the same tensor. In other words, that is exactly what we will have to do here. So, proceeding, in order to apply all we have just stated right now, we are going to symmetrize this object as we differentiate it in order to be able to have the correct result for what we want to do. So here, okay, so I think I can wind this out. So it is easy for me to say here that, so I'm just going to take this now, and this is going to be dg alpha delta comma n all over, okay, dg rho sigma comma gamma. Now this is going to be equal to 1 all over 2. So I'm going to take the first possibility I could consider, this and that. So this is chronicle delta alpha rho chronicle delta delta sigma chronicle delta n gamma. Now plus, I'm going to make an interchange. This is going to be chronicle delta delta rho chronicle delta alpha here sigma, and the last one is always the same, of course, because nothing moves that or changes it. So this is what we should have again. Okay, now what do we do about this? First of all, what do we do about this? Especially because we're going to definitely have some 2 clashing indices. Maybe not yet. Well, let's just put it back here. This or this expression, we simply replace it with that. But this is actually what we wanted to find right from the beginning. Alpha mu comma mu, the g here, rho sigma comma gamma. This is the same. So I'm going to simply just multiply through 1 all over 2, maybe make a separation, n delta, chronicle delta for that. I have alpha rho, delta of sigma delta, delta of n gamma, plus 1 all over 2, the same chronicle delta of delta n. I have the chronicle delta of delta rho here, chronicle delta of alpha sigma, chronicle delta of n gamma. Okay. Without being redundant, I'm going to try to compress this into 1 or 2 things that are similar. First of all, let me do this. Do I have a reason? Yes, I do have a reason for doing that. And this also. Now, take note of this. This chronicle delta is saying this whole term is non-zero when gamma is equal to n. And this chronicle delta is saying also that this whole term is non-zero when delta is equal to gamma. You see what this implies? It means, therefore, that this 2 gives us a chronicle delta which says that delta has to be equal to gamma for this whole expression to be non-zero. Now, if we look at this again, this chronicle delta says n has to be equal to delta for this whole term to be non-zero. But then again, this is also saying that n will have to be equal to gamma for this to be non-zero. In other words, we have another one again here, chronicle delta of gamma and delta for the whole expression to be non-zero. So in the next term, I'll simply say 1 over 2 instead of any of this, I have gamma, delta, here alpha, rho, chronicle delta, delta, sigma. And then I have plus 1 all over 2, chronicle delta of delta, rho, chronicle delta, alpha, sigma, and then of course chronicle delta, delta, gamma. Now looking at this again, I could make such a transformation as that. And yes, of course, I think I have a reason for that. Now you can see this whole term will be non-zero if gamma is equal to delta. Again, it will be non-zero if sigma is equal to delta. So the whole term is non-zero if gamma is equal to sigma. So in addition, I'm going to have 1 all over 2 here. So these chronicle deltas become condensed into some chronicle delta of gamma and sigma. Of course, like we've explained. And this is chronicle delta alpha rho plus half. Looking at this one again, the same thing is happening. You can see unless rho is equal to delta, this term is 0. Unless gamma is equal to delta, this term is 0. So in other words, unless gamma is equal to rho. So I have the chronicle delta of gamma rho and then chronicle delta of alpha sigma. This is what I get here. So the whole thing reduces to that. So I simply come back here to the expression that we had for this derivative. This is the same thing as minus. What we've obtained already for all this is going to be minus 1 all over 2. And here we have chronicle delta of gamma sigma, chronicle delta alpha rho, plus chronicle delta gamma rho, chronicle delta alpha sigma. And of course, I have here a minus, but then this whole expression is given by that. I have another minus there, which makes it all a plus half. I have some G alpha nu, and then the next thing that I have there will be the G alpha nu I'm talking about is this. And I have here with me G rho sigma and a chronicle delta of mu gamma, copying from this one result which we set aside the other time. Evaluating this chronicle delta on this expression, can we? Yes, we have a gamma somewhere here, do we? No, we don't. Do we have a mu anywhere here at all? No, we don't. But we might have as well missed this somewhere, somehow. Using one of these, for instance, we have rho and we have sigma, we have mu, we have alpha, we have nu. And where is that nu coming from? So sorry, there was a mistake here in this expression. Yeah, and it's good that I was able to catch it out here. Remember, I made a transformation here between nu and mu. And so that transformation actually wasn't just for this object alone. The transformation meant wherever, and it could have been impossible actually if it were just on this, because the second nu that made this a dummy index was on G. So we made a transformation between nu and mu by changing every nu to mu and every mu to nu. So this particular object here, which is a nu, should have been a mu, because if you remember, after rewriting this in terms of mu, nu, I said we should have to change this because we needed this object to look like this, nu, mu, nu. So we made an interchange of nu and mu on this term. And if you remember, what it implied was wherever we see nu, we change it to a mu. And wherever we see mu, we change it to a nu. And that was how we got this. And so this actually was supposed to have changed to this. So sorry, that was quite close. Now you can see that this is the same thing as plus half. G alpha, instead of the mu, I change it to a gamma, G rho sigma. Then what do I have here? This is minus of half of delta sigma gamma, delta rho alpha plus delta gamma rho, delta sigma alpha. Plus that. Of course, that gives us this expression here. Okay, the next problem might look mysterious, but it's just a simple step, especially if you can make the identification using the previous two results that we have obtained. And how do we make that happen? So I think I would like to clean everything that we just... Okay, so at this point in time, we can see, for instance, that this expression G mu nu, gamma alpha mu nu, gamma beta alpha beta, and I have here with me the G rho sigma, comma gamma. Okay, what do I have to do? Yeah, the right thing, or maybe outright thing to do here is maybe to go straight forward with some kind of Leibniz rule, have 3 terms, and then fuse around with a lot of algebra. Maybe very, very unnecessary. I can decide to, for instance, say that this is the same as the G mu nu, gamma alpha mu nu, the G rho sigma, comma gamma, multiplied here by beta alpha beta plus G mu nu, gamma alpha mu nu, multiplied here by the gamma beta alpha beta, the here I've got here G rho sigma, comma gamma. So can you see the trick here? The trick here is that I gathered 2 of these and treated it as some single object. Then by Leibniz rule, differentiate this, keep that a constant, plus keep this to a constant, differentiate that. Why do I want to do this? Because I can already see from here that I have that result as we have already obtained not too long ago. And again, you can see from this last expression that we already have something here also. Of course, it's just a matter of changing the betas to mu and all that. But let's just see how it all works out. Because in our own case, of course, just to clear every doubt, you can see here that what we have here is exactly. There's no difference, in fact, in terms of any indices, not even dummy indices. None of them are different such that we can start changing one dummy index to the other, just tweaking it just to make it look like this. So we are assured of this expression already, but this might not be that very obvious. So, but let's make it that obvious. The G rho sigma gamma. Again, remember what I said before, that even though we were given an expression, this, for instance, is the same thing as saying the G rho sigma, comma gamma. Here in the bracket is the same thing as minus 1 over 2 G. Again, to suit my purpose, because what I have here is rho sigma, I can simply make this rho sigma. Then here I'm going to have rho sigma, but then it's going to be comma alpha, because we have an alpha here. Even though it's beta beta here, of course, as you can remember, I said before, this is just a dummy index and it's contracted. So I've used something here that is quite far more convenient for me. On doing that, of course, you can see that this is the same thing as minus 1 over 2 G rho sigma. But then I get here because, of course, you remember I will have to be treating this as a constant. So I've written it out. Rho sigma is the same as rho sigma, alpha gamma. So this is the conical delta of alpha gamma. That's what we get for that. So, and that gives us that. And of course, at this point in time, we can see that on simply substituting this for that. So on this right hand side, I would like to call this object, I don't know, maybe some big U, just to make sure that we don't have to write the whole thing all out. So U is equal to rewriting the entire expression that we had for this, which was that, multiplying with this. So I would like to write this first, alpha, beta, beta. Then what I'm going to have in bracket will be minus 1 over 2, conical delta alpha rho, gamma sigma, plus sigma alpha, conical delta of rho, gamma, here plus 1 over 2 G alpha, gamma, G rho sigma. And this is what I get for the first term. And the second term, by the way, is going to be plus G mu nu, gamma alpha mu nu. And then everything here, of course, is minus 1 over 2 G rho sigma, delta alpha gamma. Okay, here at this point, we do have an alpha on this expression. So I'll simply change this to some gamma. Okay, now, well, just for the sake of arguments. Now, I would like you to see something here. Just in order to be the same or to make it look alike like what we had in the results here, this is what we have as our second result or second term. Take note that beta is a dummy index. And alpha 2 is a dummy index because if I were to open up this bracket, you see that this object will multiply this term, and this term, all separately. And there's an alpha on the affine connector, there's an alpha here, there's an alpha here, and there's an alpha here. In other words, I'm free to change any of these indices to anything else that I want. So just for the sake of conformity, I'm going to change alpha to mu and beta to nu. Just so we can have something that looks like that. So this is nu. Of course, I don't have beta anywhere else, so I'm just going to worry about the alphas. 1 over 2 delta. I said I'll be changing alpha to mu, right? So this is rho, gamma, sigma, plus mu, sigma, delta, gamma, rho. That is it, plus 1 over 2 g mu, gamma, g, rho, sigma. And that is what we get. Then very quickly, this should be minus, I believe. G mu nu, g rho sigma, gamma here. The alpha, because of this conical delta, changes to gamma. This is mu nu. And I think we are all the same. This is gamma mu nu. This is rho sigma, this is mu nu. So it's safe to say at this point that we have performed all the tests given to us. And so hopefully in the next episode we shall see more applications. So we have here, sorry we missed the factor of 1 over 2. And I guess that should be it. Yeah, exactly. Everything is just in order. So see you next time. Relax.